So tropical cyclone models are usually tens of thousands of years of synthetic hurricane history. They start with a hazard module. So hazards include the wind from the storm, we all think about from hurricanes. They include storm surge, and they also include rain-induced flood. The latter part, the rain-induced flood, is a relatively new addition to most models, but it's becoming increasingly important in the United States and across the globe. Other than the hazard module, there's also the vulnerability module, which describes, given a physical hazard, what is the resulting damage to a particular structure going to be. And then finally, there's the financial model, which takes ground-up losses from the hazard and vulnerability model and applies insurance terms, deductibles, layers, sublimits, all those things we have in our contracts to get to what the eventual loss will be paid by the insurer. An important thing to recognize is that models are complex, extremely complex. There's multiple components, multiple ways to represent the physical hazard, different kinds of models for that individual event, models we'd call them, different ways of applying financial modules, different assumptions about vulnerability, where engineering judgment plays a large role in what the eventual vulnerability is to a structure given the wind speed. What all that means is that reasonable people, reasonable practitioners, honest folks trying to do a good job will get really different answers. And so one of the things about that is it's really important to, one, understand what you're looking at, and two, often look at multiple views of risk so that you don't get fooled or you don't buy into one particular view where a practitioner made a choice, which is reasonable because you have to make choices when you build a model, but different choices result in different outcomes. And so we should all be careful to understand the impact of those choices on the risk view we have. Let's begin this discussion by talking about the physical hazard. The physical hazard primarily being the wind. Rain is also a hazard, but there's the wind, which does direct damage as well as cause storm surge. So how do we model the physical hazard? You start with the track set. So if you look at the globe, and let's take the US for an example, there's a data set called HURDAT, stands for Hurricane Data. It's supported by the National Hurricane Center from the US government. For all known storms from 1851 to present, which is a very long record in the business that we're in, it has center position, and maximum intensity from a wind point of view, usually a minimum pressure as well, sometimes additional data, including size metrics, radius of maximum wind, radius to gale force winds, radius to hurricane winds, a number of things like that. So that is your base data set for understanding the track set, which is how you go from how you get to frequency of events, making impact on a particular coastline. We use the track set to train or calibrate our synthetic history models so that they have the right amount of landfalls over the right time span in the right regions. Once we have a track set, which establishes the probability of a hurricane making landfall in a particular region over or at a particular intensity over a particular time frame. These track sets have both those characteristics as well as aggregate characteristics over a year. So if you have seasons like we just had for 2020, where we had a number of landfalls, or other seasons where we had relatively few or none. Once you have a track, the next thing you have to do is attach a wind field. So you have the storm center was here, the storm was this strong. You may have an idea it was this large. All those things are individual models, submodels to the model, which define particular characteristics of the storm. Once you have that, you have to attach a wind field. Now, again, there are lots of different ways to build wind fields. Every vendor that I know about has a different approach. They're a little related, but they're quite different. And then there are some people that use the numerical weather prediction, so a computer simulation of the physics of the storm, as opposed to an algebraic simulation, which is more typically used in the industry. In any case, you have a model which takes the central track, central pressure, central maximum wind, center fix information, size information, and converts that to a two-dimensional representation of the wind. That is supposed to represent the actual wind field that would be associated with this particular storm. A key aspect of a wind model is what we call surface roughness. So This is essentially the friction that the land and the things on the land apply to the wind field. This has a dramatic effect on winds, reducing them by 20–40% from what you might otherwise have. So if you have a wind over a very open field or a lake or something like that, it would be quite strong. If you have a wind in a urban environment or over a large forest or a very wooded residential neighborhood, those winds will be a lot lower, just because the ground, the surface is rougher, and that extra friction reduces the wind field by a substantial amount, and reduces the risk as well that these structures in these environments typically face. I guess I should be a little careful about the urban environment. That's not as clear, because we've all walked around in a major city and felt the strong gusts that happen between tall buildings. And so that is actually kind of an area of research in the community at this point, understanding how winds work in an urban environment, which is a little different than most of the risks that we think about underwriting. So you have a Winfield model, which is typically fairly simple. It'll have some kind of algebraic construct that essentially draws a circle or a circular shape, elliptical shape, describing the wind field. It'll have translation speed added. So one of the characteristics of hurricanes is that if you're in the northern hemisphere, which is where all hurricanes are, but there are tropical cyclones in the southern hemisphere as well. But in the northern hemisphere, the winds are always stronger on the right side of the storm. This happens because of the translation speed. So you add the movement of the storm to the winds, and because the winds are blowing in the same direction as the movement of the storm on the right side of the storm, those two wind speeds add, in some sense anyway, and increase the winds on the right side of the track relative to the left side of the track. That's a detail that we probably don't need to worry about too much, but it is necessarily an important thing to understand. So once you have your wind field and your roughness, you can build a map. You can build a map of the maximum winds. And this could be sustained wind, which would be typically a 1-minute average, or a gust, which is typically a 3-second average. And those different time frames, the winds, well, just to take a second here on gusts versus sustained winds. If you're talking about a 1-minute versus a 3-second average, those are going to differ by, somewhere 25–30% on average, depending on the roughness environment, depending on just the random gusts that you have. Gusts are always higher than the sustained winds. And different practitioners choose different input metrics into their models, estimates of gusts or estimates of sustained wind, usually either 1 minute for sustained or 3 seconds for gust. Once you have a map of the winds, whether it's sustained or gust, and you're trying to determine the damage trying to estimate the damage for a particular structure, you know where it is. We call it a geocode. It's specific latitude and longitude. You look up what the winds are for that particular location, and that wind field, that wind number, that wind estimate becomes input to your vulnerability function. So we're moving from the hazard from the wind to actually assessing the damage or estimating the damage that will occur to the particular structure of interest. So these vulnerability models, as we call them, are often quite complex. They're a result of engineering judgment, engineering knowledge, and a lot of calibration against claims data in the best of all worlds. So a vulnerability model will take into account what we know about the structure, its location, many characteristics of the structure that are important, the number of stories, what's the shape of the roof, is it a gable or a hip? Gable roofs happen to be a lot more vulnerable in general to strong wind fields, to hurricane force winds, than hip roofs do. Flat roofs, another characteristic. What kind of windows do they have? Are there opening protections? These things are all quite important to the eventual damage that the structure experiences. One of the important things to know about hurricanes in general, unless it's truly a catastrophic event, in which case you can have complete structural failure, homes or buildings are nearly completely destroyed. But for the most part, what we see for the damage pattern, for the most part, the damage pattern we see from hurricanes is more, there are what we call damage to the actually envelope of the building. So it's roof damage, it is window damage, doors. And those things are often significant, but not catastrophic from a structural point of view. But what happens is you lose a few shingles, you break a window, you lose, in a more severe case, you lose a chunk of plywood off your roof, and then it rains a lot in hurricanes. And so you have the combination of the damage from the wind plus exceptional damage from water getting into the home from rain. And that is often the principal mode of damage in a storm, is a combination of some physical damage to the outside envelope plus enormous damage interior from the rain that follows. I want to take a moment to talk about the frequency of storms that are occurring in the Atlantic. Now, there's a debate within the industry, and there has been a debate in the industry for almost as long as I've been, which is a long time, since early part of the 2000s, 2005 being when this really started. So the mid 2000s, I guess I should say, about whether we should use frequency assumptions for hurricanes that are reflective of the current environment, or whether we should use long-term statistics, which are typically for most of the commercial products, starting the hurricane record in 1900 for the United States. So you have 120 odd years of record that we believe is the most credible for setting the actual frequency of events that happen to the country. Now, if you've been living and working in the industry for the last years, you've seen, particularly recently, exceptional levels of landfalling activity far above the normal thing that we expect. Just to put that in perspective, the normal kind of hurricane season, the average hurricane season 1900 to present, has about 10 named storms, so storms that have a name to them. 6 of those reach hurricane strength, and typically 2 to 3, average is about 2.5 of those become what we call major hurricanes, which means they're Cat 3s or stronger. Atlantic sea surface temperatures today are really higher than they've ever been measured to be in the past, in the recorded history that we have. We know from looking at the historical data as well that when sea surface temperatures in the Atlantic are warm, you have more hurricanes and you have more intense hurricanes. So it makes sense, there's some people in the industry believe it makes sense, and I'm one of them, that if we know the Atlantic sea surface temperatures are warmer, then it makes sense for us to increase the risk, increase the frequency of hurricanes in our model. And this is often referred to in 2 different ways. There's some vendors will call it a warm sea surface temperature sensitivity test. Other vendors will call this kind of a medium-term rate perspective. But the basic notion is that we understand that the sea surface temperatures over the Atlantic are warmer than they have been, and that this has physical consequences for hurricanes. They're stronger and more frequent. One of the interesting things about this is, why is the Atlantic warmer? And there are competing theories around that. There is something called the Atlantic multi-decadal oscillation, which is a natural physical process that's been going on presumably forever, that leads to decadal variability in Atlantic sea surface temperature. And for a long time, it was generally believed that variability in this AMO, Atlantic multi-decadal oscillation, was the driver of warm sea surface temperatures we're facing today. There's an alternative theory, which is a combination of global warming, so climate change, as well as pollution. So you have the last really cool period we had was in the 70s and 80s, 1970s, 1980s. And that turns out to be a time when there was a significant amount of air pollution that reduced the amount of solar energy reaching the surface and resulted in a reduction in temperature. And then we clean that up. And now the cleaner air plus global warming has led to a fairly substantial increase in sea surface temperature. And there are some that believe that that's the primary driver of the increase of temperature and thus the increase in hurricane risk. Regardless of what you believe on that, the core fact is that sea surface temperatures are warmer than they have been, and that results in more hurricanes, more frequent hurricanes, and more intense hurricanes. I want to take a second for a tangent here and talk about units. So physical units for measuring wind speeds. They vary in both sort of the base unit, whether it's a knot or a mile an hour, and those are about 15% different. And then they vary over averaging time. So there's 3-second gusts, 1 minute sustained, 2 minutes sustained, 10 minutes sustained. And depending on what you're looking at, anemometers are often, for instance, 2-minute sustained or 3-second gusts. Reporting centers, the National Hurricane Center reports in 1 minute sustained. The JMA, the Japan Meteorological Agency, which is the primary agency responsible for typhoons in the Western Pacific, they use a 10-minute wind. So these things, and 10 minute to 1 minute is another 10% different. So the important thing here is that when you're looking at wind speeds from storms, and you're making, particularly when you're making comparisons, it's quite important to make sure you have the units lined up, that you have the same averaging time and the same units. If you compare 1 minute winds to 3-second gusts, and one is in knots and one in miles an hour, it's not going to make any sense at all. And I've seen it more than once lead to fairly massive confusion about what's going on. So when you're looking at wind speed measurements or wind speed reports about a storm, just take a moment and make sure that you have the units and the averaging time known and the same for both all the information that you're comparing. So let's take a second and talk about transitioning events. Now, when hurricanes are in the southern part of the Atlantic, so south of, say, 20 or 25 degrees north, they're what we call a tropical cyclone. They're a tropical system. They are extracting their energy that makes the wind speeds directly from the heat from the ocean. Now, as they move north, the ocean waters cool off quite a lot. And once they get below about 26 degrees Celsius, they're just too cool. The ocean surface becomes too cool to supply the heat the hurricane needs. And when that happens, you end up with storms start transforming. They're transforming from a hurricane type of physics to a more traditional weather type of physics, where instead of drawing the energy from the ocean, they draw the energy from the surrounding atmosphere. So when this is going on, when the storm is transforming from a hurricane, which draws its heat from the ocean's warmth, to what we call an extratropical system that draws its energy from the rest of the atmosphere, we call those transitioning storms. And they're quite common. Essentially all storms that are north of, say, 25 or 30 degrees north are in the process of transitioning. And so they're quite important when you're trying to understand the risk that you face in places like North Carolina or New Jersey or New York or any of New England. As well as if you move outside the United States, then you're talking about lots of Japan. Transitioning events are actually quite important to the risks that they face. Now, one of the important things about transitioning events is, along with the change in the way the storm derives its energy, there are significant changes in the structure of the storm, both from a rain and a wind perspective. So the winds tend to be a lot more asymmetric, with much stronger winds on the right side of the track than on the left side of the track. Now, you also have changes in the rain, and typically a transitioning event will have more rain than a normal tropical cyclone, or at least a larger footprint of the rain. So the physical hazard you're facing from a transitioning storm in, say, the New England region is typically quite a bit different than the physical hazard that someone in Florida, say in Miami, would experience from a normal hurricane or a tropical cyclone. So let's take a moment and talk about storm surge. Storm surge is a significant part of the physical hazard associated with many hurricanes. Wind fields are always part of the hazard, and depending on various characteristics of the storm and the local environment, storm surge may or may not be a major player in the damage and threat to life associated with a hurricane. Now, one of the things about storm surge that's important to understand is that it's not just about the wind speed. So when you think about physical damage from a storm to a structure from wind, all that matters is how strong the wind is. When you think about storm surge, a lot of other things matter. And those things can be bigger storms. If your storm is wider, it will typically have more surge than a smaller storm. There's an interesting thing that happens with how fast the storm is moving. Storms that are moving around 10 miles an hour tend to maximize the storm surge. And there's some physical reasons for that, but we don't have to get into that discussion for this for this particular note. The local bathymetry and shape of the coastline makes an enormous difference to the surge. So if you have if you think about the shape of the bottom of the ocean as it approaches land, so there's the shoreline, there's typically something we call the continental shelf, which is a relatively shallow region that extends off the coast for quite a ways. And then there's the deep ocean where it's thousands of meters deep. So if your continental shelf, that area of the ocean that's adjacent to the continent, adjacent to the shoreline that is relatively shallow, if that's really wide, then you end up with lots of storm surge. If it's really narrow, it actually becomes more difficult to generate a storm surge. So characteristics of the local ocean bottom also matter quite a bit. Then another thing that's important to storm surge is the shape of the coastline itself. Bays and estuaries tend to focus water, both from the rain flowing down as well as the surge pushing in, and you can have quite extreme surges, and often in the heads of these bays and estuaries. Then if you have hooks or little areas where water gets stuck and can't propagate away, can't flow away, then those can be very significant regions. One of the classic examples of that is the Louisiana Butte, which traps storm surge in that little cup around New Orleans. And then you have the same thing, we saw it in Hurricane Sandy, in the New York area where storm surge gets trapped in that little cup of the coastline there around New York Harbor. So the shape of the coast matters to storm surge quite a lot as well. So one of the things to say that really about the storm surge that I was trying to drive home there is when you think about storm surge risk, recognize it's a local phenomenon. The shape of the coastline and the shape of the surrounding ocean bottom matter quite a lot. The size of the storm matters, the movement speed of the storm matters, and the intensity of the winds matter. So when you think about storm surge, recognize a lot of things matter and don't focus on the wind only when you're trying to understand the risk you face. To this point, we've been talking about hurricanes and thinking of them really as landfalling things alone. So the storm makes landfall, it has a certain wind speed, and we really stopped talking about it at that point. But a really important characteristic of hurricanes is how fast do they weaken as they move inland. We call this decay, storm decay, and it's typically modeled with an exponential decay. It's not really important how that's done for this conversation, but just recognize that they do weaken and that there is a lot of variability in how quickly that weakening happens, depending on a number of characteristics of the event. Smaller storms, so if they're narrower in size, tend to weaken faster, and wider storms that have bigger storms that have a bit more energy tend to last a little longer. Transitioning storms tend to weaken more slowly. All these things matter, and so that has a big impact on how far inland you have to worry about the hurricane actually causing significant damage. A typical hurricane will lose about half of its wind speed in the first 12 hours after landfall. So that's a lot. If you have a 100-knot storm, after half a day, it's typically 50 knots or so. There's a lot of variability around that, and different things matter in terms of how that comes out. But just understand that storms weaken at about that rate, about half their wind speed over the first 12 hours after landfall. And then you ask the question, well, how far inland do I have to worry about damage? And then that is a combination of how quickly they weaken and how fast they're moving. If you have a storm moving at 10 miles an hour, in 12 hours, it moves 120 miles, right? If it's moving slower, then it decays at kind of the same rate. So the decay is more a function of time than distance. Really focus on how quickly it's moving when you think about how far the inland damage is going to propagate. Thanks, bye.